In this talk, we discussed determination of the residual error parameters of a VNA when there's low resolution in the time domain. And just to give you a bit of context, this is part of a larger research thrust of ours, which is to reduce the cost of verification in general and, where possible, to automate verification. As compared to the examples in the previous presentation, this is a bit more of a complex example. We're going to discuss getting super resolution in the time domain using the methods discussed earlier. But since you all were in the earlier talk, you're fully prepared to digest this content. And again, so just as a bit of motivation, we all know that increasing demand for information services delivered over wireless infrastructure has driven a lot of competition in the marketplace, has made testing sort of a critical success factor. And to the extent that lower cost measurement systems have emerged, including portable equipment, embedded test systems, and VNAs, up to about 10 gigahertz now, these systems must still be verified. And despite the reductions in the cost of some of the test instruments, verification can still be costly, especially at lower frequencies when the cost of an airline can be larger. And especially on wafer as well. So this will be familiar to all of you, I'm sure. This is a one-port VNA model with an error box consisting of an ideal VNA and a distorting adapter with 3 unknown parameters, directivity, tracking, and source match. After calibration, down below, the model comprises a distorting adapter, but the difference is that we now have residual error parameters. And the objective of the content here and of the paper is to estimate these residual parameters. So the conventional algorithm uses time domain processing. So to separate the residual signals in the time domain, precision verification line is used with a short to allow for separation in time or equivalently length. And that's sort of illustrated down here below, where the directivity does not experience the delay of the line. The residual tracking error does experience the delay of the line twice, and the source match experiences it 4 times. And so using time domain processing, it's possible to separate out these various reflections and to estimate their magnitude. And here we see that distance frequency model for measurement of the residual using the line and the short. And you can distinguish the 3 components at the 3 different delays. But in general, they have unknown frequency properties. So it's necessary to determine the frequency response of each reflection. The frequency step is chosen according to this formula. And interpolation between those frequency points is achieved using a cubic spline interpolation. There are, of course, other methods of interpolation, but those are not considered in this paper. And we should note that one constraint of the cubic spline interpolation method is it requires at least 3 points within the VNA's operating frequency range. So at the top of the slide here, we see the sort of building blocks or the process for the classic algorithm for filtering in the time domain. FT here is Fourier transform, right? And impulse response analysis is performed. And then, so basically with the help of the inverse transform, the measured frequency response is transformed into an impulse response. And then we analyze the impulse response in the time domain by determining the appropriate time delays for further calculations. And then those sections of time are selected or deselected in the time domain. And after filtering, we transform those back to the frequency domain using the Fourier transform. So in this approach, the situation is complicated when the conventional algorithms cannot distinguish the reflectors from one another. And this can occur when we are operating in a lower frequency range of measurements or over a narrow band of frequencies as well. Or in general, when the frequency range is small compared to the length of the line. So as an example, consider the impulse response below here. It's really impossible to identify and separate three distinct reflectors here. We see really only one reflector. So to solve this problem of estimating the residual parameters from the measurements, we instead propose to use an iterative estimation based on Markov theory and nonlinear filtering. So we should choose the state vector to represent the underlying dynamics of our system. And then we also need to determine a observation equation. So the state vector x is related to that observed function z via the function h, plus a factor n to represent the measurement system noise. And since in general this function is nonlinear, methods of linearization sort of necessarily lead to an introduction of a methodological error. So we need to use a nonlinear filtering, which can be implemented with a relatively fast algorithm. And we chose to use the unscented Kalman filter, sort of as building from the first presentation. The unscented Kalman filter assumes the underlying values of the parameters of the state vector are time invariant. And that's reflected in the state equation here. The parameters are assumed to be constant, not changing in time. The only quantities that change in time are, as the algorithm iterates, are our estimates of those state values based on the observations. And here's the overall unscented Kalman filter in a block diagram format. And here we see our familiar friend now, the unscented transform. It's actually an unscented transform extrapolation in this scenario. So with each iteration of the algorithm, an observation is fed in here at z, and it's compared to the predicted observation based on our estimates of the state variable. And then based on the estimated state, the covariance matrix is passed through the gain and multiplied by the next observation, and this whole system iterates through all of the observed data, all of the measurements over frequency. So just to summarize the approach here, the algorithm is estimating the frequency characteristics of two or more closely spaced reflectors, closely delay-spaced reflectors using Markov theory. And it's convenient to use a numerical algorithm, and in this case we chose the unscented transform, leading to the unscented Kalman filter algorithm. So here we have a description of our experimental setup. We have 3.5 millimeter coaxial waveguide, a VNA, a set of standards, and a precision airline. The VNA is calibrated with the standards, given a polynomial approximation of the standards across its full frequency range. We used a short open load calibration. Again, we're talking about one-port measurements here. And then the VNA is connected to the airline and the short, and the measurement is performed. That's the measurement result here versus frequency. And we take as given the parameters of the line, the length and the material properties. And the short parameters are also taken as given. They were measured actually after TRL calibration in this case. So the frequency response is then used to calculate the impulse response using the inverse Fourier transform. And that's shown down here below. We perform this calculation with two different frequency ranges. So when the frequency range, including all of the data up to 32 gigahertz is included, the transform is at this red shape below, where we can see clearly the three reflectors in the time domain, and they could be separated easily. But by artificially limiting the frequency range to 8 gigahertz, we achieved the blue trace here, which is basically showing us it would be impossible to resolve these separate reflections at this lower frequency given this airline. So this is the result of the algorithm. On this slide, we see the calculation of the residual directivity, the parameter D, according to different methods. When using the time domain method, a well-known effect occurs, which is called the Gibbs effect. This results from our selection of the windowing function. Obviously, a windowing function is chosen to select the time domain or the time response portion of interest and to reject the others. The other reflections can be considered to be interference to the reflection of interest. But whenever, regardless of what window function is chosen, you still see some distortion at the edges due to the window effect, the Gibbs effect. In the case of the unscented Kalman filter algorithm, our algorithm is in some sense choosing those windowing coefficients on its own iteratively, and basically adapting according to the data to reject the interference from the other reflections. And then just to provide some commentary, the results match quite well between the unscented Kalman filter algorithm and the time domain method. To the extent they deviate from the characterization of the load here, we attribute that to a sort of shortcoming of the load's characterization above 7 gigahertz. But the comparison between the two methods over the frequency range up to 8 gigahertz is below minus 70 dB, which we thought was quite good. And then moving on to estimates of the source match and the reflection tracking for the two frequency ranges. The results here are also quite good. At the upper end of the 8 gigahertz band, you can see some deviation of the unscented Kalman filter algorithm. This results from the fact that we only took into account measurements up to 8 gigahertz in estimating the parameter at 8 gigahertz, whereas with the full frequency range, measurements taken between above 8 gigahertz, say up to maybe 10 gigahertz, have a non-negligible effect on our estimate at 8 gigahertz. So we're sort of working with half the data at that point. And you can sort of consider this to be an analog of the Gibbs effect in our case, but the magnitude of the deviation here is less than would be expected from the Gibbs effect in the conventional algorithms. Okay, and then our second experimental setup was an on-wafer measurement. And this slide describes the experimental setup, starting from the VNA, the probe station, and ISS. First, the VNA was calibrated with the ISS across its full frequency range, and the calibration performed was LRRM. And then the VNA was connected to the ISS kit with an open at the other end. And we took the parameters of the loaded line as given. So since we're focusing our work in this paper on the qualitative performance of the proposed algorithm, we took the liberty of a few simplifications. For example, we assumed that the radiation of the open stub was negligible and that the characteristic impedance of the line was matched with the system reference impedance. If you were doing quantitative measurements, you might take the extra step of impedance correction. But again, since we're looking at sort of the relative qualitative performance of the algorithm, we did not take those extra steps. And so here are the results of the estimations of the residual parameters for the on-wafer system. You can see that the result is about minus 35 in the case of directivity, and reflection tracking is less than 0.05 of a dB. In this case, there really is no benchmark result to compare our algorithm's performance against. But the calculation results appear to be realistic, and we would say that the ripple of the loaded line seems to be what we would expect, and there really are no abnormal results in this output. So the proposed new method estimates the frequency characteristics of the individual reflectors even when there's a very low resolution in the time domain. And it is of particular use when a long line is impractical, either because the frequency range is low or in any other situation where resolution of the conventional time domain methods is poor. The residual errors were calculated by processing the measured reflection coefficient of a single device, and the effectiveness was shown in cases of coaxial and on-wafer measurements here. And the method is of particular interest when we need to verify a low-cost measurement system. Thank you.